So, Threadripper launched in November. Well, kind of. Threadripper launched in November, but not Pro. I mean, Pro kind of launched in November, but you couldn't buy it. This 96-core Falcon Northwest system I've had. Today, we're going to do a deep dive on Unreal Engine, starting with my beefy Falcon Northwest rack system that has 96 cores and a terabyte of memory. We need to do a deep dive because Threadripper 7000, the launch, it's been... I mean, theoretically, you could buy the processor, but you couldn't buy this motherboard until a few months ago, at least the Asus one, and then the ASRock over here, that's just a couple weeks ago. So what's going on with that? There's Pro and non-Pro. Non-Pro, you've been available for a while. There's also Linux because it's Unreal. So our Falcon Northwest system with 96 cores, CPU madness, full disclosure, they sent it to me, but with a TRX 50 motherboard. I bought the WRX 90 motherboard that's in here, and also the terabyte of Kingston RAM. Aye, my great-grandfather had an axe. He handed it down to my father, who replaced the handle. He handed it down to me, and I've replaced the blade. But it's been in my family hundreds of years. So yeah, it's still... I mean, there's stuff in here from Falcon Northwest. This is similar to how you would get a system. This is the rack mount version. They have tower versions as well. But this is not the only kit of memory that I tested. We also tested about 5 kits from Kingston, about 3 kits from G-Skill, down to a positively pedestrian 128 gigabytes of memory. First world problems, right? 128 gigabytes of memory? Yeah, basically. Look, if you're an Unreal developer and you just want something that works without thinking about it, then you should just head to Falcon Northwest's website because it's going to outperform any Dell, HP, or Lenovo OEM systems that are based around the same parts because it's Falcon Northwest. And they didn't sponsor this video exactly. I mean, they did contribute some of the parts here, but like, this system is me. Even the motherboard, I bought it because I could get it sooner buying it than asking ASRock to send it because it's a lot of fun. And also, I have an addiction. You've seen the movie The Burbs, right? I may have gone full Rumsfeld on pulling on the old wallpaper. And so I also bought 3 other Threadripper systems. And these are non-Pro Threadripper TRX 50 systems. 32 cores, 64 cores. Get the ASRock board, the Asus board, and the Gigabyte board. All 3 TRX 50 flavors. Every different memory combination you could think of between the gaming memory, a DDR5 6000, and our JetX standard 5200, well 5600, but running at 5200 because that's just how we roll. 128 gig DIMMs. It's a little challenging to get 512 gigabytes of memory on TRX 50. It's expensive, but it can be done. Yeah, those are the non-Pro systems though. These are the Pro systems because there's only 2 Pro motherboards I can get right now. We get the ASRock WRX 90, and we've got with and without the TPM module in hardware. And then for the TRX 50 systems, we have Gigabyte, ASRock, and Asus again. Yeah, I think that classifies as an addiction, or an affliction, a blessing and a curse. First world problems. Unreal Engine is what we need to test, and specifically the game Path of Titans. They've been kind enough to let me run a bunch of build testing and do a bunch of stuff over the last few months while I've been struggling with Threadripper Pro parts, also experimenting with Threadripper non-Pro TRX 50. This game spans many, many platforms, and it's a real game. And the dev happens for them, for the developers, mostly on Windows because that platform has the most reach for cross-compile targets versus Linux. Although, I've got a few tricks up my sleeve for Linux and make it run really fast. Let's take a look at the results. Okay, so there's actually kind of a lot to unpack here from the results. Like, this is sort of baffling. I mean, okay, we're starting with Path of Titans, and we started with a compile time of about an hour, a little over an hour, on an older 32-core Threadripper 5000 platform. But I was able to optimize the process there and get it down to about 40 minutes, at least on Linux. Now, I didn't expect that we'd get to our best case scenario compile time of 9 minutes. I mean, from like 69 minutes to 9 minutes, that's quite an improvement. And that's clearly not just throwing hardware at the problem. Yeah, there was some software optimization as well. Part of the reason this took me so long is because there can be so much difference between the Pro and non-Pro Threadrippers. I was surprised by that for the developer workload because historically Threadripper had so much memory bandwidth, even with 4 memory channels, that moving to Threadripper Pro, I mean, for creative workloads, okay, sure, the expectation is that more memory bandwidth is more better, obviously. But for creatives, yeah, I mean, but what about developers? This is CPU cache. Mostly the developer stuff lives in CPU cache. At least for Unreal, it seems like Unreal really likes having more memory bandwidth. But the results are also surprising. If you look at the 24 core, that was enough to make me buy a Pro Threadripper. This is 24 cores, so I could do 24 cores to 24 cores. And the 24 core and the 32 core have the same number of CCDs, so you'd think it's the same amount of memory bandwidth. But for Unreal, it seems like Unreal suffers a little bit from moving from 24 to 32 cores, more than you would expect. But 64 cores and 8 memory channels, oh, that's the sweet spot. And yeah, you can get a lot done with 96 cores as well, don't you worry. Terabyte of memory, oh boy, that helps. Running with only 128 gig of memory though, it doesn't cut it. And it turns out there was 2 interesting things going on with 128 gigs of memory. One, on Windows, 128 gigs of memory, and this is wild, was a better experience than Linux. Clearly, I'm doing something wrong. Well, it turns out that I didn't have stuff turned on in Linux that I probably should have had turned on in Linux. And that is compressed memory. That's on by default in Windows, but you need ZRAM in Linux. So here's the first place, compiling Unreal on Windows. Way better experience. Now, diving into our results, one of the surprising things about the Unreal Engine setup here is that it's a little different. And this is basically just a summary of data. This is not all of the data that I had from this. Unreal Engine is different than like Chromium tests, Chromium Compile or GCC or Clang or something like that. And maybe this is because this is a real world project. Maybe this is because I tweaked things like whether or not we're using Unity building or Unity's build process, because you get individual like targets, I guess, which are useful for debugging. Like there's a bunch of variables here. And I didn't want to get too lost in the weeds. Bottom line, this is a surprising result because 8 memory channels makes more of a difference than I thought it would, but optimizing the build process so that I'm not waiting forever on testing is also kind of a factor here. So you look at these results and it's like, everything's about 20 minutes. It doesn't matter what you buy. There is some truth to that, but if you have to run 100 builds for 100 different platforms and you save 5 minutes per build, that's a pretty big savings. So, well, it cuts both ways because it's about 20 minutes across the board, no matter what you look at. Now, the 96 core, the gains from 96 cores and 8 memory channels from 64 cores and 8 memory channels, well, 64 cores is the sweet spot. The thing that's interesting is the fall off from 32 to 64 cores. With 32 cores, we have half as many CCDs, and that seems to cause some suffering for us when we're talking about 8 memory channels. When we're talking about 4 memory channels, there's almost no difference between 24 and 32 cores for Unreal. And this is not true with something like GCC or LLVM or Chromium or any other compiles like that, because you got 8 more cores per CCD, and all of that's going to factor in, and that's going to be a thing. At the same time, you do have the same amount of L3 cache because you have the same number of CCDs. So the cores in the CCDs in Threadripper Pro 7000 are so good that you really want to have 8 CCDs to keep everything fed. Or possibly AMD should have done like the double link between chiplets and CCDs for Threadripper, the way that they do for some of their F-series EPYC CPUs. I'm not really sure. I'm not really sure what to make of that. And running everything from a RAM disk, and this is basically so the output products go to a RAM disk as well as the input products, with a terabyte of memory, with all of the tuning stops that I can pull out and changing some of the compile parameters, I can get this down to about a 9-minute and 29-second build. I don't think that's very realistic. I think our real spread here is from 16 minutes and 42 seconds on the 512 gigabyte configuration on our 96 core, all the way down to 39 minutes and 4 seconds on our 24 core, which is not a dramatic improvement over our 49-minute best case scenario compile time on the 32 core 8 channel Pro 5000 series AMD. To go from 49 minutes to 24 minutes, you're basically cutting your compile time by half by optimizing your environments and having everything basically be a well-balanced configuration. Now, there's also the question of NUMA nodes. Does NPS 1 or NPS 4 make more sense for this job? And when you've got 8 memory channels to work with, it seems like NPS 1 is a little bit better result than NPS 4. NPS 4 is going to be more memory locality for each different thing that you're doing, and maybe if you're not using the Unity build system, using the like setting that to false in the build target thing so that you get all the different debuggable objects, okay, maybe NPS 4 makes more sense in that scenario. But yeah, bottom line, sweet spot here, 8 memory channels, not 128 gigabytes of memory, because you're going to slow your build time down by half in a worst case scenario, even if you've got 64 cores. Even just compiling Unreal Engine itself, like that is a test. It's not represented in the numbers that I've shown you, but just compiling Unreal Engine itself on a Threadripper Pro with 128 gigabytes of memory versus say 384 gigabytes of memory, it is almost twice as bad. Memory timings, CCDs, everything else. Like, it's not just memory channels, it's also having the cores to keep the memory channels busy. So 24 cores and 8 memory channels, I think most things that would use 8 memory channels are going to be a little problematic with only 24 cores. You need more CCDs apparently to keep that DDR5 fed. When we run 8/64, we get just under 300 gigabytes per second on the memory benchmark read bandwidth for our Threadripper Pro 96 core machine, fully loaded 8 memory channels. Whereas it's about 171 gigabytes per second on our Threadripper non-Pro TRX 50 systems. That's not half. So, I mean, on paper, it's only a third slower, roughly. And we kind of do see that in the compile results. Like, the compile results are a third-ish slower sometimes. The most interesting result for this might be that the mythological 48-core Threadripper could be a really amazing fit for software developers that need memory and everything else. The other disappointing thing here is that I really expected to be able to tell you, relegate your Unreal Engine build processes with, 20 fewer threads than you have, and then you'll still enjoy an amazing dev experience while you're doing something in the background. But the TPM stutter, or whatever that was, doesn't make that into real actionable advice that I can give you. The other thing that I really hoped I would be able to tell you is to just, reserve 20 cores and then run your Unreal Engine compile in the background and still enjoy a screaming fast workstation. But the TPM stutters, or whatever that is on Windows, make that not actually actionable advice. If you want to run Linux as a host operating system and Windows as a VM, then the stuttering can be relegated to a Windows VM or whatever. I didn't test that. But I did test Unreal Engine compiling under a Windows VM with most of the cores passed through to it, while also doing Unreal Engine development on a Linux host. And while I was on the Linux host, I didn't notice any stuttering. I don't think there was stuttering on the Windows virtual machine either, because TPM would be implemented a different way when it's virtualized like that. But that's maybe something that could be another video or another test, or depending on your interest, engage below or on level 1 forums or something like that. But I really expected to be able to tell you, it's like, yeah, the consolation prize for, you need more than 32 cores, but 64 cores is maybe too many. And so I expected to tell you the consolation prize is, we'll just use 48 of your cores for the Unreal process and keep the rest of the cores so you can keep doing dev while you got stuff running in the background, and you'll never know all that stuff's running in the background. But because of the stutters, it doesn't work that way. And that might be something that can be fixed with a BIOS update or something like that. But since I experienced it on both ASRock and Asus, I don't know, probably not. A second conversation here is that our CPUs are now so fast that they can compress and decompress things while they're waiting on main memory. Like, that seems like that would be low-hanging fruit to make memory faster, right? I mean, while we're waiting on the memory subsystem, the CPUs are so unbusy that they can compress and decompress memory. And actually, with the 4-channel Threadrippers, the compressed memory let you theoretically claw back some memory bandwidth for this specific kind of a job. So like if you're doing compiles and it's splitting off a bunch of threads, yeah, the compressed memory really helps with that sort of a job. And Linux starts to edge out Windows again on Unreal Engine compiles using ZRAM. It does take a little tweaking, but that's a really interesting conversation. Now, I should have had this video out months ago, but the reality is that it's actually been kind of hard to buy Threadripper Pro in the DIY channel, and I've been a little concerned about that, especially if you look at the BIOS offering from Asus. I mean, I could buy the motherboard in January, but there's also not been a BIOS update since January, and the ASRock WRX90 board literally just hit retail a couple weeks ago. That is well after the November launch in 2023, right? Like, what gives? Something weird going on there. Although Lenovo, HP, and Dell have been able to sell a lot of systems. So maybe because they're selling systems, they get first pick? I don't know. It's really weird. Now, on the other hand, non-pro Threadripper systems have been a dream. I've been running those 3 systems basically continuously since November, doing different jobs on Windows and Linux. And it's really nice to see the kernel updates, especially kernel 6.1, AMD and their developers, like, they're really starting to hit things in stride to be able to help manage this multi-core madness in a way that is not happening at Microsoft. It doesn't seem to be, and that's concerning. But from kernel 6.1 on a 96-core platform to kernel now 6.10, which is at the bleeding edge at the time that I'm doing this video, it is so much better on Linux. I mean, we're talking about 10% performance improvements cumulatively, maybe more on some workloads. Now hold up, in case you want to throw a tantrum about Windows being slower than Linux, when you depend on the operating system for things like managing primitives and threads and memory management and NUMA and that sort of thing, don't tell me that changing the scheduler is going to make all these problems go away. You are wrong. Windows has the core scheduler and the root scheduler. This can have a big impact on some kinds of workloads. Yes, that is true. The root scheduler was added mainly for Hyper-V virtualization, where Hyper-V virtual machines performed laughably bad because, well, hyperthreading and how that was working under the hood was contributing to thread contention. But now today, the root scheduler is part of the client operating system, at least if you enable memory security and other Hyper-V features, because it provides better isolation between the operating system and user processes. Technically, the root scheduler was only supported on server OSs. You can use BCD edit to change that, and that's something we can discuss further on the forum. But also unrelated to the scheduler, Windows has this insane idea they call processor groups as a way to add support for more than 64 threads without hopefully breaking legacy applications and legacy compatibility. But that's led to all sorts of fun performance regressions, some of which probably are at play when we're talking about these high crazy core count and thread count systems. Now, to be sure, Linux has also had its share of growing pains, managing and manipulating lots of cores and threads and even I/O, but much more progress has been made there by Team Penguin than Team Redmond. If you want to set your own scheduler parameters, it's merely a make menu config away from you in a custom kernel compile. Now, this is slightly harder than just running BCD edit on Windows to change from the core scheduler to the root scheduler, but it's also much less impotent. Don't worry, I know that Microsoft is actually working on real honest-to-goodness scheduler improvements and other Windows internal stuff, which strangely is also going to be part of Windows 11. They're not even going to call it Windows 12. It's just going to be an upgrade to Windows 11, because they know they got problems with processor groups and everything else. They know. Now, 4 memory channels versus 8 memory channels, that's the star of the show, but that's not all there is to memory. You might think, okay, TRX 50, I can claw back some of the speed I'm losing out on because I've only got 4 memory channels versus 8 because the memory's 20% faster in terms of clocks. That's not exactly true, but it's not exactly false either. Running the memory beyond JetX speeds, that's beyond, well, 5200, technically not a JetX speed, but 5200 is what it's rated for. On the Threadripper Pro platform with 8 memory channels, real challenge, wouldn't recommend that. Not a lot of fun, especially with the lack of BIOS updates from ASUS. Did I mention the lack of BIOS updates from ASUS? I think I have. I tried various sets of Kingston DDR5 registered ECC as well as our G-Skill kits ranging from 128 gigabytes to 1 terabyte. Now, in contrast, the non-Pro TRX 50 platform was stable at DDR5 6000 and with much tighter memory timings, which really did help claw back some performance and make up for the lack of memory channels. That plus memory compression, that really brings it home for me on the TRX 50 platform, especially on Linux. Now, with all that background and context and rambling, let's flip back to our results. 256 gigabytes for the 24 core, still kind of oddly slow. Like 32 cores and 256 gigabytes of memory is going to be your starting point. And again, thank you to our patrons and our Floatplane subscribers and viewers like you for making this video possible, because I wouldn't be able to do this if run all these systems simultaneously and scrounge together hardware, although some of the memory and stuff is borrowed from some members of our audience. So thank you also in order to do this testing and put it together. And bottom line, I was kind of surprised that Threadripper Pro, even for compile and dev type jobs for something as large as a real shipping Unreal Engine game, it made that much of a difference having the Pro platform versus 64 cores on the non-Pro platform, at least for this one specific game. Overall, both Threadripper 7000, well, the Pro and the non-Pro 7000, I guess, they're incredible performance for developers, period. Especially, specifically, Unreal Engine. With the right setup and tweaks and tuning, you can achieve phenomenal results. 9 minutes versus 69 minutes. If you are using Linux and you're not using ZRAM on machines like this, I think you're probably leaving a lot of performance on the table. Have you tested it? You know, what has your experience been with the ZRAM on Threadripper 7000 series? Heck, even 5000 series. I get why some distros are turning this on by default. I also want to do more deep dives like this, and to that end, that 24-core Threadripper non-Pro system, I'm sending that to Glenn Berry. We're going to show that Microsoft SQL Server has been suffering over the last 2 years over this thread scheduler nonsense. Both the core and root scheduler, it doesn't matter. We pointed it out ages ago. It's processor groups. It's a headache for the whole Microsoft family. But that's going to have to be a video for another time. Looking forward to that. Be sure to check that out. I'm Wendell, this is Level 1. This has been a quick look at Unreal development on a whole bunch of Threadripper systems, but this is only just the beginning, I think. I want to hear from you. Engage below and/or the Level 1 forums. All right, I'm signing out and I'll see you there.